Let me remind you what it looks like. That's acetic acid. We already did that with the structure. Well, let's work on the VSEPR shapes now for this. And then we're going to draw it correctly according to the shape. So in its three-dimensional form. Start with the first carbon here. All right, EG for electronic geometry. How many groups? Count 4, so we call this tetrahedral. And all right, Mg for molecular geometry. Because there's no lone pairs, it has the same name. All right, now let's go to the next one. This carbon here, we have to do this for all central atoms. So that would be all atoms that are bonded to 2 or more other atoms. Any atoms bonded to 2 or more other atoms, we have to do shape. Okay, so this carbon, electronic geometry, how many groups? Count 3, the double bond counts as one group, so we call this trigonal, planar. And the molecular geometry, because there's no lone pairs, is the same. Oh, let's also write the bond angles. Trigonal planar is what angle? 120 degrees, 360 divided by 3. Tetrahedral, you could derive this, but it's a little easier just to memorize it. It's 109.5 degrees. Okay, and then let's go to the last one. This one right there. How many groups? Should see 4, 2 lone pairs and 2 single bonds, so that's tetrahedral. And then Mg, the molecular geometry, there's 2 lone pairs. Anybody know what that's called? There's 2 lone pairs, it's called bent. 2 lone pairs on a tetrahedral. Still the same bond angle as the other one, 109.5. Okay? So we've done all central atoms. That's all atoms that are bonded to 2 or more other atoms. Okay? So now let's try to draw this. On Scratch over here, let me just remind you, a bent would look like this. There'd be an atom here, here, and here, and there'd be 2 lone pairs. That's what a bench would look like. And what else? A trigonal planar will look like this. Okay. And then a tetrahedral will look like this. The atom in the middle, and 4 atoms around it. Okay, there's a tetrahedral. So those are the shapes, or the templates of the shapes we're looking for. For the tetrahedral, the triangle, we call that a wedge. The wedge is coming out of the board into the classroom. The dash is going into the board, into this other room behind you. And then the ones that are lines, just straight lines, those ones are in the plane of the screen. Okay, so this tetrahedral would be this right here, where the wedge is this one coming towards you, the dash is this one going away from you, and these 2 are in the line. Okay, try to draw this craziness here. I'm going to redraw that. I recommend starting with the tetrahedral one first. Okay, so that's a carbon. I'm going to kind of repeat this sort of look right there. I'm going to do one at a time. There's a first carbon bonded to the second carbon. Okay? I could have put anything on any side. It wouldn't really have mattered. And then the next one is trigonal planar. Doesn't matter that the oxygen's pointing down. And then the next one is bent. There's the molecule. There's acetic acid. With the correct shapes. Any questions on how I did that? Okay, make sure you can do that before we get to the final. The next one we wanted to do after this was HClO3. Let's try that one. This one I believe we haven't done in class before, so we'll start from scratch. HClO3 valence electrons equals 1 for hydrogen, 7 for oxygen, and 3 times 6 for, 7 for chlorine, and then oxygen's in column 6, there's 3 of them. Okay, so that's 18 plus 8, that's 26. And let's see what we get. Cl surrounded by 3 oxygens. And I don't know if you remember the hint I gave you before, but where should that hydrogen go? Yeah, this was on a previous class. I said that if you have an acid, this is an acid, it's actually one of your stronger acids. Acids, the hydrogen will typically go on an oxygen if there is an oxygen. Okay? So that's always a good guess for any of the strong acids. We've seen, just like acetic acid up above, notice the acidic hydrogen went on the oxygen. Okay? That's you'll learn more. You'll learn why that's true in Chem 2B, but for now, true. Okay. Draw the skeleton 2, 4, 6, 8. That's all the single bonds. 8 of 26 electrons so far. 10, 12, 14, 16, 18, 20. Okay, I've done 20 of 26. Now I'm going to go over to the other oxygen. If there's oxygens, I always like to go to those first, if they're internal. Now I forgot where I was. 20, right? Is that what I said? 20, 22, 24, 26. Now, everything actually has an octet. We feel good about that. Let's check our formal charges. What's the formal charge of that one right there, that oxygen? Should get a 0. It's in column 6, and there's 6 items around it. 1, 2, 3, 4, 5, 6. That's 0. How about either of these oxygens? They're both the same. You should get a -1 out of here right now. 1, 2, 3, 4, 5, 6, 7. So these are both -1. How about that chlorine? Yeah, chlorine's in column 7, but there's only 5 items around it. 1, 2, 3, 4, 5. So it's +2. Do we like this fluid structure? No, it's horrible, because we don't want a +2 formal charge. What we're going to do is pick one of these and scratch it out, and we're going to make a double bond to try to fix that. We can do that with chlorine and break the octet, because chlorine is below the carbon row on the periodic table. So if you look at the carbon row, chlorine is below it, so we can break the octet having an expanded valence shell. Okay, now what's the formal charge on chlorine? +1. Yeah. It's in column 7. You count 1, 2, 3, 4, 5, 6. It's short by 1 electronic species, so it's +1. This is a fine structure right there. You can get one more, which I'll draw to the right, over here somewhere. So this will be a resonance structure. I could bring another lone pair in from the oxygen on the left-hand side. Maybe that. Which atom here has a non-zero formal charge? Which one's not 0, if any? You find anything that's not 0? Should be getting 0 for every single atom. Should be getting 0 for every single atom. Do we like that? Yeah, we like that a lot. They're both resonance structures. They're both fine. This one We don't like how it breaks the octet so much, but we can handle that. So this one's a really good one. But either way, we can move on now to do the VSEPR shape. So there's two central atoms now. That atom right there, how many groups? E.g. for electron group, there's 1, 2, 3, 4. So this is tetrahedral. 4 groups, but the molecular geometry with one lone pair is called what? Trigonal pyramidal. Again, if you need to refer to your reader still, that's fine. It's page 90 where we're getting all these shapes. If you're a little fuzzy on them right now, that's fine. Got a little time to learn them. Okay, what's a bond angle? It's still 109.5 because of the tetrahedral. Okay, now let's do the other central atom. It's right here. Okay? E.g. electron geometry, there's 4 groups, 2 lone pairs, 2 single bonds. This is tetrahedral. I'll abbreviate that. And then the molecular geometry, because 2 are lone pairs, just like the previous example of the acetic acid, this is bent. Still 109.5 degrees. Okay, we need to try to draw that. So let's try that craziness. First, I'm going to draw the tetrahedral because it's a more complicated shape, so I like to start there. There's the tetrahedral template. And now you can do the lone pair a couple different ways. See, there's one lone pair on the chlorate. You could either do this, and that doesn't mean that the bond really exists. It's just showing there's a lone pair on that side. So this doesn't count as an electron bond here, 2 electrons. We're just showing that that's where it is. Or if you prefer, you could erase this whole thing and just put 2 dots here. So the second option would be to just put 2 dots here. And so what you're trying to do is make something, if you take a tetrahedral, take one of these off. You're trying to make something like this. So the way I've drawn it is this way. Okay, one's coming out at you. You could have also drawn it this way or this way. However you want to show the shape is fine. So another option for this would have been put the 2 dots on top. Okay, so both are fine. All right, I'm going to just continue with the one I started with though. So I'm going to continue with the one on the left. Okay, 2 of those oxygens are double bonded. Doesn't matter which 2 you pick, just pick any 2 on the tetrahedral. And then this one is bent. So just make sure it does not look linear. Make sure the 2 bonds look at different angles, and that would be the final structure. If you were doing this one, it'd be a little harder to draw, but I'll show you what it would look like if you did it from this perspective. Same answer. The hard part is to show the double bond on one of these, and the way you would do that is do a double wedge. Show a double bond. So both of these would be the same answer. Just depends on the perspective at which you're looking at the trigonal pyramidal. Are you looking at it this way, or are you looking at it this way? Any questions on these pictures? Yeah? How would you show the double bond for the dash? You'd make 2 dashes parallel to each other. Like that. So I try to keep, the reason I did this picture on the left, or I prefer this one slightly, it keeps the double bonds in the plane. Whenever you can keep double, triple bonds like that in the plane, it just looks less ugly. Okay. If we didn't have any, then it wouldn't matter, and I probably would prefer the one on the right. Okay. Questions? All right. True. Okay, I posted this online. Let's take a look at it. We're not going to do the polarity part yet. We'll wait until I say more about polarity. But let's just run through these. This one, how many groups? 4. So the electronic geometry, write this down if you want to know on the printout, if you printed it out or somewhere else. I'm not going to write it down. Electronic geometry would be tetrahedral, but one is a lone pair, so that makes it trigonal pyramidal. 109.5 degree bonding. Both carbons will be the same over here. 3 groups, we call that trigonal planar. And since there's no lone pairs, the molecular geometry is also trigonal planar. So the bond angle for that is 120. Okay, this one, same thing, 3 groups. It's trigonal planar for the electronic geometry, but what is the molecular geometry? Bent. What's the bond angle? 120, because it's from a trigonal planar. Okay, we did something kind of like this. The electronic geometry for oxygen, carbon, and nitrogen are all what? All tetrahedral, because they all have 4 groups. They all have 4 groups. But the molecular geometry are all different. This one's bent for molecular geometry. This one's tetrahedral, and this one is trigonal pyramidal. All have 109.5 degree bond angles. Let's try another one. This one, how many groups on that iodine? Should count 6 groups on the iodine. That is called octahedral. For 6 groups, octahedral. 2 of them, as you can see, are lone pairs. So, anybody who has their sheet out, 2 lone pairs on octahedral is called what for molecular geometry? Square planar. It's actually drawn square planar right now. This one has 5 groups. What's the electronic geometry called? 5 groups. Trigonal bipyramidal. So it's the one that looks like this one. It's like this. 2 groups here and 3 groups around it, like that. If there's 1 lone pair on a trigonal bipyramidal, the molecular geometry is called seesaw. Yeah, it would be as if you removed one of these bonds. Let's do that, and it forms a little teeter-totter seesaw. Okay. It's not drawn to the correct shape, but it's seesaw. All right, this one, how many groups? 6. We just did this one. 6 groups is octahedral for the electronic geometry. Molecular geometry, 2 lone pairs is called square planar. Same for the one on the right. Octahedral square planar. Bond angles are 90 degrees. Try a few more. I just want to make sure you got this. How many groups? 4, so it's called tetrahedral. Same for the molecular geometry, also tetrahedral, 109.5. Okay, this one, 5 groups, so that is trigonal bipyramidal. When 2 are lone pairs, the molecular geometry is called T-shaped. It's actually drawn correctly. It is T-shaped. Thus the bond angle is 90. This is an octahedral here, but 1 is a lone pair, so it is called what? Yeah, the molecular geometry is square pyramidal. What's the bond angles, by the way? For octahedral, it's 90. Okay, we did one like that. That's a repeat for some reason. Here's an octahedral. Every single one of these carbons has what geometry? Every single carbon has 4 groups, so it's tetrahedral. Okay? So they all have 109.5 degree bonding. What is what? What is this called? I think there's a question in the front. Anybody? Octane. 1, 2, 3, 4, 5, 6, 7, 8 carbons octane. So you've heard of high-octane gasoline? Not exactly this, but something like this. All right. So you might not have those names down. Just make sure you're getting more used to them over time. We are going to continue in polarity, though. We want to started it last time. This is page 92 and following in the reader. Oh, for those of you who like to check off things. Oh, we only have, after this, 2 more classes left. Wow. You're almost done with Chem 2A and me. Unless you take me for 2B. I apologize for your suffering. Okay. So page 92 in the reader. In the textbook, this is page 379 and following. I'm going to explain this a little bit differently than the textbook. If you follow the reader, I think that might be the easiest. You'll see in the reader there are 4 methods I outlined to determine if something is polar. You can also say, does something have a dipole, or does something have a dipole moment? All the same. There's 4 methods. Let me give you, I'm going to cover in class, so the book covers method 1 in the reader. I'm going to cover in class method 3 and 4. The book doesn't cover methods 2, 3, or 4. They're just my own additions. But I'll cover method 3 and 4 in class right now. And if you need more information, definitely go to office hours. Okay. Method 3, memorization. If you're not visual, it takes the most brain space, but yeah, you don't have to visualize something. I wouldn't recommend this method, but some students have to go there. It will hurt you in OChem the more you cannot visualize. So visualizing is helpful in future classes, especially OChem and otherwise. So, memorization is adding the last column there on the right. Is it polar or non-polar? And it tells you the answer. Okay? Some of them, you have to think slightly more. But basically what you'll notice, if something does not have lone pairs on it, then it might be non-polar. If it has lone pairs, it's likely polar. So let me show you what I mean. Lone pairs, polar. Now I'm talking about the center atom only. Lone pairs, polar. Lone pairs, polar. Lone pairs, polar. Lone pairs, polar. Here's an exception, and here's an exception down here at the bottom too. This one is square planar. But for the most part, if it has lone pairs, it's polar. Again, what is polar? It's an unequal distribution in electrons. So those lone pairs cause an unequal distribution. If it doesn't have a lone pair, you have to decide. So for example, linear, it's non-polar only if both groups, that's the outermost groups, are the same. And the rest stay the same. Non-polar if all groups are the same, non-polar if all groups are the same, etc. So if all groups are the same, and it's one of those, then you'll know it's non-polar. If the groups are not the same, then it would be polar. So that's the memorization. You're memorizing this last column on page 90 of the reader. Again, not what I recommend, because it'll be more difficult later if you take more chemistry classes. Okay, so let's do method 4. The next method I'm going to describe is the symmetry method. This is visual. Remember, polarity means, is there an unequal distribution of electrons? Is there polar covalent bonds? So you look at something like HBr, here's the Lewis structure. You just look at it, you ask yourself, is it asymmetric? Hopefully you say yes, because on one side there's a bromine, and the other side there's a hydrogen. If it's asymmetric, it's polar. It's polar, it has a dipole moment. It has a net dipole. Look at something like water. It's bent. Okay? It's polar. It's asymmetric. There's hydrogens on one side, but not on the other side. The other side has lone pairs. This is polar. I think I showed you the example last time of CO2, carbon dioxide. It's symmetric. There's oxygens on both sides. This is nonpolar. It has no net dipole. It has no dipole moment. Nonpolar. Br2. It's nonpolar. It's symmetric. It has bromines on both sides. It's nonpolar. So you're looking for symmetry. Let's do a trigonal pyramidal. Ammonia. It's asymmetric. There's hydrogens on the bottom, but there's a lone pair on the top. Totally asymmetric. This is polar. Those of you who are doing memorizing, lone pairs on central atoms, like these last two, are going to lead you towards polar. This also, I think I gave you the water-oil example last time. If you are a female or maybe a male and you wear fingernail polish, okay, and you want to remove that fingernail polish, water's not going to do it. You can't just put your fingers under water. That fingernail polish is not going to remove. The reason is fingernail polish is organic. Most organics are non-polar. And water is polar. So polar and nonpolar will not mix. You need something nonpolar to wash off the nonpolar. And so to do that, you use acetone, which is fingernail polish remover. If you've ever worked in a mechanic shop, they have like a solvent rinse where you can kind of rinse the grease off of machinery parts. The grease is organic, it's nonpolar. So you can't just go with water to try to rinse off the grease. You need something else nonpolar. So they have a solvent in there that will rinse off the grease. So this is where this kind of fits. Polars don't mix with nonpolars, and vice versa. Nonpolars only mix with themselves, polars only mix with themselves. Why? Because these have unequal distributions which are attracted to each other, just like magnets are attracted to each other. These are essentially neutrals, which are attracted to each other, but are not attracted with someone with an unequal distribution of electrons. So you need to be able to determine for any molecule, is it polar or non-polar? The big key is you must draw the VSEPR shape before determining if it's polar or non-polar. Especially if you're doing the symmetry method. Okay? If you're doing the memorization, I guess you don't necessarily need to do that. So here we go. This is back. I hope you printed it out. Alright. Let's start with this one. You might be ready to tell there's a lone pair on the center atom. It's going to be polar. The first one on the left is polar. I'll just redraw it really quickly. It would look like this. It's asymmetric. So whether you memorize it or just looked at it, it's polar. First one's polar. Let's do the second one. What do you think about the second one? Definitely non-polar. It's fully symmetric. What's on the right is on the left. What's on the top is on the bottom. Or you could have said, from the memorization, that it's trigonal planar and it's the same groups symmetrically. So this is non-polar. And most organics with carbon and hydrogen are non-polar. Okay. This isn't okay. Let's do this one first. This one's a little more thinking. Okay, let's do that one. Polar or non-polar? I don't even have to draw it really. It is polar. There's no way that could be symmetric. There's a nitrogen on one side and an oxygen on the other. There's no way it can be symmetric. It's totally funky looking. So this is polar. Polar. Okay, let's do the next one. What do you think that is? This is polar. Why? Yeah, it's asymmetric. Sometimes people ask, okay, but it's all oxygens. But that lone pair on the top does cause a electron distribution to be off. So this is polar, even though it's all oxygens. Let's do another one. Ooh, I like this one. Let's do this one right there. This is polar. And it's polar because if you drew it, this would be seesaw, and you would see that it would be totally asymmetric. There's chlorines on the right but not the left. It's polar. Okay, so this one's polar. All right, this one? This one is actually nonpolar. The squared planar, if all four groups are the same, is nonpolar because it's fully symmetric. It would be like removing both of these blue groups. It's fully symmetric. So this one is nonpolar. Okay. How about this one? Oh yeah, let me point to again this one. It's also square planar like the previous one, but that it is not symmetric. It's not symmetric. This one on the left is polar, but this one is nonpolar. So the polar on the left, the nonpolar on the right, because the one on the right is symmetric. The fluorines are symmetric and the chlorines are symmetric. So this one on the right, again, is nonpolar, while the one on the left was polar. Any questions before I go to the next page? Okay, so for any molecule, now these, the Lewis structures are drawn out. Imagine a problem where I had you draw the Lewis structure, do the VSEPR, and then figure out polarity. How about this one? Oh, sorry. This one. Wait, let me redraw it. Let me redraw that one. What if I do this? What if I did it that way? Polar or nonpolar? What's the shape of this? Tetrahedral. You better draw the shape to really double check. Polar or nonpolar? This is definitely polar. Because bromines are on one side and chlorines are on the other side. Let me show you with a little stick diagram here. This is polar. Don't be fooled by this. This is not the correct shape. You should not be looking at this. It is not drawn to the correct shape. You must only look at correctly drawn shapes to determine symmetry. It is this. Okay? My fingers are on the chlorines. Okay? My fingers are on the chlorines. Bromines would be these blue spheres here. So you can see it's asymmetric. Bromines are on one side, but chlorines are on the other side. Totally not symmetric. A tetrahedral will only be nonpolar if all groups are identical. Okay? Tetrahedral will only be nonpolar if all groups are identical. Only be nonpolar. I hope I said nonpolar. Okay, let's see. We did a couple other of these. How about this one right here? Polar or nonpolar? That one's polar. It's asymmetric. There's an oxygen on top. Polar. How about that one right there? Polar. This is also polar. That one right there, the arsenic one, because it's asymmetric. Chlorine on the right, but no chlorine on the left. This is definitely polar. It's totally asymmetric. Now, let's do that one. It is non-polar. Again, most organics, that is carbons and hydrogens, are non-polar. And it's fully symmetric. Even though it's long, it's got that same symmetric zigzag with the carbons and the hydrogens. So this is non-polar. And in fact, a carbon-hydrogen bond pretty much is considered non-polar or fully covalent. There's really almost no ionic character in it. So, non-polar again for the last one. Any questions of this second page? Okay, make sure any molecule, and I want to turn your attention, let's see, to the reader here on page, let me find the page here, page 95. I want to turn your attention to page 95. We've done everything on the left, so let me see if I can zoom in a little closer. Not everything, but a lot of the things. So you should be able to draw a Lewis structure, count the groups, figure out the number of lone pairs on the central atom, and go from there to shape. You should be able to use the VSEPR table, find the electronic molecular geometry, and then, oops, I need to zoom out a little bit, redraw it so that you have the correct Lewis structure according to the shape. You should be able to do all this down here in the middle. Now from the geometry you should be able to figure out the bond angles, and you can use the VSEPR table until the final. And then you should now be able to figure out polarity. Okay, and I have the symmetry method described here in this box. So most of the things, especially in the middle, you should be able to do now. Yeah.
Do double bonds, do single bonds, that symmetry, like you have a single bond on one side and a double bond on the other. Is that symmetry?
The question is, if there's a single bond on one side and a double on the other.
Let's say it was symmetric, if it had both singles, but what if you had a single on one side?
Yeah, he's saying if it's symmetric, if they're both single bonds, but then if there's a double on one and a single on the other. I can't think of an example where that would exist, but if you think of one, let me know. I don't know if that hypothetical situation exists. Yeah, so you might not run into it. Well, let me know if you see one. Maybe if you think of a carbonate ion. Well, first, any questions on this? Okay. There could be an example, however, where you get this sort of structure. And he's asking about polarity here. This is trigonoplanar, this is carbonate. I believe we already did this in class. CO32 minus carbonate ion. This would be nonpolar. It's totally symmetric. But it's symmetric mostly because of resonance, because the double bond could be here, or there. So it goes everywhere. But the case where you're talking about, I don't know if there's one where it would just stay on one side. If you think of one, let me know, we can look at it. Yeah, this would be nonpolar. Okay. And for the ion just itself. Alright, let's move on. A little bit more of this chapter before we go to the next one. But luckily, it's all the easiest stuff. So this is going to be page 94 in the reader, and in the textbook, 94 in the reader, 382 in the textbook. Luckily, we've got the easiest stuff right now left over. This is sections really 8 and 9. It's BO, bond order, BL, bond length, and BE, bond energy. Bond order, bond length, and bond energy. Let's do bond order. Let's say we have two atoms that could have a single, a double, or a triple bond. The bond order would be 1, 2, and 3. It's a way to put a numerical value to a bond. Meaning a single bond has a bond order of 1, a double bond has a bond order of 2, triple bond order of 3. Can we have bond orders that are not whole numbers? It seems like no, but yes, we can. You've seen one before, I just never pointed it out before. This one has 3 resonance structures. Here's another one. And here's another one. Okay, there's the three resonance structures. Let's focus in on one of those three bonds. Let's say this one, which is here and here. Okay, I circled it in black. Here the bond order is 1, here the bond order is 1, and here the bond order is 2. But a resonance structure means it's always changing. So the bond order on the lower left is the average of those three. Sometimes it's 1, sometimes it's 1, and sometimes it's 2. Divided over three structures, this has a bond order of 4/3, or 1 1/3. So here's an example. Whenever there's a resonance structure, you can have a bond order that's not a whole number. But typically, as you might think naturally, yeah, the bond orders will be whole numbers. You'll see examples in the next chapter where a bond order also could be not a whole number. But again, when there's a resonance structure, you could have a bond order that's not a whole number. That's bond order. Bond length is just the distance between two nuclei. So there's not much to say about that. And then bond energy, the stronger the bond, the more energy is stored. So for example, a triple bond, this one here, will have more energy, more bond energy, because there's three bonds in there. A double bond will be in the middle, and the lowest would be a single bond. It would have the lowest amount of energy. Just one thing to know, and you'll see this in the next chapter, a double bond is not twice as strong as a single bond. And a triple bond is not 3 times as strong. The reason is, these bonds are not all identical. And you'll see why in the next chapter. So, one last thing to do with this section though. Okay, let's draw a continuum here for bond order. Bond order goes basically, let's say, from 1 to 2 to 3. As bond order increases, as I mentioned before, bond energy will increase. So a triple bond has more energy than a single bond. However, the bond length is going to be the opposite of those two. It's going to increase the other way, meaning a single bond is the longest. Because a double bond is so strong, it pulls the atoms closer. And a triple bond is even stronger, it pulls the atoms even closer. So a triple bond is the shortest bond. A single bond is the longest. And if you kind of follow the pattern, triple bond the shortest, then you go double bond's longer, single bond's longer, and no bond is infinite. So it follows that pattern. If there's no bond, they're infinitely far apart. Let's take a break. We're done with that chapter.